think about signs. What have we said so far about signs? I think the only definitive thing we said is that K, kinetic energy, is always positive. Can anybody think of an exception to that? One exception. Outside the box mathematically, what is the exception? Zero, very good. Now we're starting to get along. It's always positive or zero. Okay. But W can be negative, work can be negative. Right? So the force, if the force slows something down, I'll show you in a minute, the force can be one way, the displacement can be the other way, and you get a negative work. So if you have a negative work, how can K always be positive? And the answer is because it is the difference of K. So if we're thinking about signs, K is positive, work can be either way. It is equal to delta K. So K is always positive, kinetic energy is always positive, but it can decrease. That's the idea. K can go down. So in most energy problems, you're always working with differences. And differences can always be negative, even if the value has to be positive. Okay? My number of whatever is always positive, but I can have it decrease. So let's do a problem that uses this idea. Okay? Let's think about this problem. Here we've got a mass M approaching a spring at V naught. And here's the spring. Sitting here innocently at its natural length. We're going to call that the origin on this x-axis. And we're going to say, how much does it compress the spring? All right, it's flying in. The spring is clearly going to push back and stop it. How far in does it go? So I'm going to write spring stops mass, how far? So how far does spring decline? You could do this with Newton's laws and kinematics, with F equals ma. In principle, you could. You'd say, I just need the acceleration. I know I have V naught squared, or the V final squared, I have V initial squared, plus 2AD. So if I just plug in the acceleration, I'll get D. But acceleration is not constant. That's the problem. This is not a constant acceleration situation. The spring's force depends on position. So you can't even integrate it with respect to time. Because it depends on position. So this would be a hard problem you have to deal with. Differential equations and stuff. Or you can do it with energy. Right? Let's do it with energy. Let's say the work that the spring does, F dot dx equals delta K. W equals delta K. And let's make the system the mass. The system can move. It doesn't have to sit still. Okay. So let's see. So we would say, okay, let's do the integral first. Let's see. It's the integral. The thing is going to go from 0 to d. From 0, the thing we're looking for is in the limit of the integral. Oh my God. A little teeny bit of calculus-based physics here. What is the force on the mass? Well, it's minus kx. Hooke's law. So write it. Minus kx. And now check it. If we go to positive x, do we feel a negative force? Yes. Okay, you did it right. Very good, Jason. Thank you, God. I just want some coffee. And then we say equals what? Kf minus ki. Oh, no. Minus ki. And then you just go to town. The calculus part, the fun part. Minus 1/2 kx squared. Minus 1/2 kx squared from 0 to d equals, what is k final?